Blythe Towal is our next speaker, Neuromorphic Engineering at Qualcomm. This is going to be terrific. An engineer, she works at the intersection of biology and technology and defines how the brain works. That's pretty good. And so she's an engineer. Let's hear from her.
So hello. First of all, I just want to say thank you for inviting me to speak. I feel quite honored to be here. And I do want to tell you today about neuromorphic engineering at Qualcomm. But before I get there, I thought I should tell some of you who Qualcomm is, who may not know, and how I ended up there in an industry position. So Qualcomm is a fabless semiconductor and telecommunications company. They make basically computer chips for cell phones. So if you have a cell phone in this room, something that Qualcomm made is in it. And they actually are quite a big company now. We just beat out Intel in terms of market capitalization in the semiconductor industry. So if you haven't heard of us yet, you will be hearing about us. And what that means, and the relevance will become clear later, is that it's a company that's in a great position to make a big impact in how we think about computing hardware and computing technology in the future. So how did I end up there? I grew up sort of in the academic environment. I've always been an engineer, so I started out as an electrical engineer at Georgia Tech, interested in robotics and system and control engineering, which is what I got my degree in. But like many people in that field, I had a revelation one night that it's really hard to tell a robot to do something, and it's really easy to tell a human to do that, or even an animal, a dog. And I sort of got interested in the nervous system that way, in the brain as a control system, if you will. And so, many people here have an interest in the brain from more of a medical perspective, but mine has really been more of a proof of concept that a lot of these control strategies can be done in very efficient ways. And so that's how I sort of look at the brain. And I went to do my PhD, and I did sort of nitty-gritty neuroscience experiments, recording from single cells in live animals, while they were doing things to really get a handle on the neuroscience and understand some of these circuit and system level algorithms that I thought the brain was using, if you'll allow me to say that. And then, for my postdoc, I went to Caltech and I worked with someone who was very good at, looking through the neuroscience literature and really taking a lot of these things that I had learned and distilling them down into mathematical concepts that we could really then, once you have an equation for something, it's very easy to take that back over to the engineering world and say, let's build it like this. So at the end of my postdoc, I was looking at, what I wanted to do next. And I have to say that I feel very privileged now after being here and hearing some of these stories that I really, I had a happy story getting to that point. And I really felt, I didn't have a lack of confidence. I really felt I could do it. I felt I was prepared to go into an academic faculty position. But at that point, I happened to have two other opportunities crop up. One was in industry at Qualcomm, and one was at a nonprofit institute, the Allen Brain Institute. And, so I was in a very great position. I feel very privileged that was the case, but I basically got to compare and contrast these three options for what to do next. And I sat down and I decided that what I should do is think about what I could get done, what kind of research I could do, how impactful that would be, and what my life would look like in those three options. And honestly, industry won, hands down, for what I could do. And part of the reason was that there was a project at Qualcomm that pretty much was fitting exactly into what I wanted to do and what I would have wanted to do in my lab. But the type of research I wanted to do was sort of this, hybrid of neuroscience and engineering, and really translating between the two, which requires an interdisciplinary approach. It requires a lot of facilities and things like that. And while I knew that would be possible in an academic environment eventually, I wasn't sure that while I was getting tenure and having to worry about all those things, that I could really do the same kind of research and have the same kind of impact as if I joined this team at Qualcomm that already had everything in place. I was working with teams of engineers that were all qualified and wouldn't disappear in 4 years after they got their degrees, and so on. So anyway, in the end, I decided to end up at an industry at Qualcomm doing neuromorphic engineering. So I'd be happy to talk more about that with anyone if you're interested. But I did want to bring up one point, which was that while I was making this decision, I had very few people I could talk to about options other than academia. There was, we've been talking a lot about how you should encourage women to go on and move on in science. And for me, what that meant was that people were encouraging me to go on in academia, which I think would not have been the right decision for me at that point. And so, there wasn't a lot of visibility to these opportunities outside. I just happened to be in a good position to see them. And I have, to this day, a lot of my friends who are still in academia being like, how did you decide to jump off that cliff? You can never come back. You're gone forever. And, I did have some of those thoughts while I was there, and I was lucky enough to realize that that was not the case and went ahead and took that leap. But I think that's something that we could do for both men and women, is to make those other opportunities clearer. And, if you're not in a good spot, there are lots of places to move, not just other academic institutions, but lots of other types of institutions. So anyway, on that note, I'll tell you a little bit about neuromorphic engineering. First of all, what that is. Second of all, why it's important, and what we're doing at Qualcomm with neuromorphic engineering. So for any Latin buffs in the room, you may have realized that my title is missing. Let's see, I don't know how to get that back. But anyway, it's not terribly important. It just says, what is neuromorphic engineering? And it just means shaped like the brain. So neuromorphic is really just something that's shaped like the brain or inspired by the brain. And when we say engineering, what we mean is we want to build things that are inspired and shaped by how we think the brain works. And this is not necessarily a very new idea. It's been around for a while. Very long time. These are just two examples of it that sort of span the gamut of what we mean when we talk about neuromorphic engineering. So at the algorithmic level, those of you familiar with computer science have probably heard about artificial neural networks. And that was one very clear example where it allows you to build algorithms where you set up a series of nodes and the connections between those nodes. And the nodes typically do things very simple, like take sums of all their inputs or look and see if the amount of input is above a threshold. But the connections between them have weights that can change or strengths that can change, very much like what we think a synapse does. And these type of algorithms are very much inspired by the brain. People looked at the brain and said, let's build something that looks like that, at least at an abstract level. And they ended up being very, very useful if you needed to write an algorithm to compute a very complicated function, or if you had a series of inputs and outputs and you didn't know what the relationship was between them, but you wanted to continue computing that relationship, you could train this network by providing it with the inputs and the outputs, and with very specific training algorithms, you could adjust the weights so that this network would approximate basically an arbitrary function that maybe you didn't know or maybe was just really complicated and you didn't want to write it down. So that was a very big impact. And that's very much at the algorithmic level. So looking at the brain and saying, what's the algorithm it's running? And here's how we do that. You can also go down and think more about the implementation level. And this was done probably most famously by Carver Mead, who was actually at Caltech, where he was thinking about actually building neurons in silicon. So one thing you can ask when you go down to this implementation point of view is, why transistors? Why not just build some sort of neuron as a sort of fundamental unit of a circuit instead? And what can we do with that? Is it useful? Can we do anything exciting with that? So that sort of spans the gamut of what you might include in neuromorphic engineering. There's lots of other things. And we at Qualcomm are really excited about these ideas and taking them one step further and trying to look at the whole spectrum here. But before I get to telling you about exactly what we're doing at Qualcomm, I wanted to tell you a little bit more about why should we do this. You might argue that, my computer keeps getting faster and cheaper and smaller every year, and I don't have to do anything about it. I used to have a phone that I could make phone calls on, and now I have a pocket PC that I carry around with me, basically. And it's a valid question, because this has a lot of cool factors, especially for people like me. But why do we need to think about this type of computation from an engineering perspective at all? And I don't have a whole lot of time. I could talk for a long time about that. But I did want to give you 3 specific reasons for this. And the first one is probably something all of you have heard of, or if you haven't heard of it specifically, you may be familiar with it, and I learned last night that actually some of you may even know the guy who invented it. So anyway, it's Moore's Law, and it was invented by Gordon Moore, who's one of the co-founders of Intel. And in 1965, he predicted that you would get more and more transistors on a processing chip as time went by, and specifically that there would be an exponential relationship there. So every 2 years, you would double the number of resistors. And the black line is basically what he predicted in 1965, just be up here. And it turned out to be true. So these dots just indicate different processors. So you may, like an Intel Pentium chip, and so on. And basically, he's been basically right up to this point. We've seen these exponential growths in the processing power that we can really get on a CPU, which is great. But as you may have guessed, this can't go on forever. There is a there may be a fundamental limit that we reach with this, and that limit comes down to what this law actually is talking about. So on the right here, I've showed you a block diagram of a transistor. And you don't need to know what all the pieces do. All you need to know is that basically Moore's law is talking about the fact that the distance between those two red blocks, the source and the drain, is getting smaller. That's predicting that we'd be able to come up with better manufacturing processes to make that gap smaller and smaller is what the law boils down to. And so, you don't have to be a neuroscientist, a rocket scientist, or a computer scientist to realize that, those might get too close eventually. And that is indeed what people predict will happen, and various people have various opinions on when exactly that's going to happen. But certainly when you get down to the atomic scale, you're going to have to deal with a different type or a different range of electromagnetic forces that may change the operation of that transistor and may not allow us to sort of continue using these as currently we are. So I've just converted Moore's law here, or actually borrowed a graph from someone who's done that, where I'm showing the distance between these two things on the y-axis in time along the x-axis, and you can sort of see where we are. Where we are right now is about right here. And so we're still an order of magnitude or so larger than at the atomic scale, but we're getting there. Predictions range, there are all sorts of predictions, but certainly by 2050, people think we'll be down to that scale. So what do we do at that point? What that means is that all of these gains in technology that we've been seeing, all of these shrinking computers, they get faster and cheaper and everything, that is not going to be sustainable anymore. We're going to have to do something different. And various people have lots of different opinions about what we do at that point, but one of the options is neuromorphic engineering. If we can build something that operates with a different sort of fundamental unit that's not a transistor, we may be able to get around this particular fundamental limit. Now, neuromorphic engineering is not the only option. There are others out there. Quantum computing is something that people have thought about. Just figuring out better algorithms for parallel computing are other options. But I wanted to point this out, as this is one of the reasons that big technology companies, especially like Qualcomm, are interested in neuromorphic engineering. The second reason I wanted to give you is that you all know this. Your brain can still do things that computers can't. There are many examples of that. I think a couple of my favorite ones are robust walking. If you put a bipedal robot on an arbitrary terrain, it still can't walk very well. That's a problem we haven't solved. Yet it's something that humans and other animals learn to do very, very easily. Language acquisition is another one. No matter how long I speak English to my computer, it's never going to learn English. It's just not going to happen. Visual recognition is another one where we've actually made lots of strides. Computer vision can do lots and lots of things, but it still can't solve those little like number and letter things you have to put in to get into websites, those little CAPTCHAs. Still can't solve that. And I also wanted to show you one other thing that computer vision still can't do, but you can do. So I'm going to play this video for you, and I simply want to ask you, is there a cat in this sequence of images? Okay, so everybody saw the cat. So that's something a computer still can't do. We've made lots of progress, but there are a number of reasons computers still can't do this. One reason is that they're line drawings, so they're very sort of semantic drawings. Another reason is that it's happening too fast. So these sorts of problems, I hope you can see how they might be applicable in the computer science world, and there's still things that our current algorithms can't do. So neuromorphic engineering is really asking, is there an algorithm in the brain we haven't discovered yet that will allow us to solve these problems? The third reason I wanted to give you has to do with power efficiency. So at Qualcomm, because we make things for cell phones and tablets and mobile things, we're very concerned with power efficiency. Whatever chip we build has to be very, very low power. And that's been a concern, all throughout, but it's becoming more of a concern because we are having more demand on these devices, and there are more and more applications which you might consider always-on applications. So for example, most of you are probably familiar with Siri, which is Apple's personal assistant, but you still have to press a button to talk to Siri. Whereas you might imagine an application where you could just put your phone somewhere and just say, like we like to say at Qualcomm, "Hey Snapdragon," which is our flagship chip, and it just responds and acts like Siri, the personal assistant. But this requires the phone to always be on and have some amount of power dissipating all the time. And so those types of applications are becoming more popular and more useful. So the brain, if you think about it, people have done the calculation and figured out how much power our brain supposedly works. Now this is a back of the envelope calculation. You can't stick a multimeter up to your brain and figure out what it's using. But Gwebena Boahen at Stanford has figured out that the brain uses about 20 watts of power to operate, or that's about 24 cents per hour, which is much, much lower than the current state-of-the-art technology. So the brain may have, in addition to algorithmic things that allow us to solve new problems, it may actually just be a better implementation that allows us to solve many of the same problems, but at much lower power. So those were the three reasons. So I hope I've convinced you that it's worth studying. And now I'm going to tell you a little bit about what we're actually doing with this at Qualcomm. So one of the first decisions we had to make is, you look at the history of what's been done here, and we had to decide, what level of abstraction do we want to think of the brain at? Because you could get mired down, we could model it at, the subatomic particle level. We could model it like many computers, psychologists and artificial intelligence people do at a very abstract level. But we wanted to sort of aim for something that was builds on the past work in terms of learning algorithms, but allows us to do a richer set of computations. And so our first design choice here was to work with spiking neurons. That's what it says at the top. So spiking neurons are models of neurons that instead of sending a value at every time step, so that's what an artificial neuron, most of the networks will basically output a value at every time step. What a spiking neuron does is it only sends a signal every so often in the form of a spike. And that's one very important thing for power, because it means rather than trying to send something every time step, you just have to send things every so often. And if we can figure out the coding strategies that allow you to do computation in that way, that could give us a huge savings in power. So to give you a little bit of a better idea of what I mean by that, if you think about real neurons, they produce these electrical signals. That's sort of a voltage trace up there. And the big vertical lines are the spikes. And basically, you can model this as a series of coupled differential equations. And by changing some parameters, you can get all the different patterns that you see in the middle there by changing the parameters and the specific input currents. And so spiking neurons allow us a richer set of behaviors than the traditional artificial neural networks will allow. And so once we have made this design decision to go with spiking neural networks, we then needed to develop a series of tools to operate with those networks in software and also in hardware, where we're using field programmable gate arrays, which are fun little devices, to do that. So that was sort of one step of this project. The second design choice we made was to go with a digital implementation. So the work I mentioned at the beginning from Carver-Mead really looked at an analog implementation. And that has a number of problems that ended up being sort of insurmountable for that type of approach. And so we've decided to go with a digital design where we're actually clocking things and working at that sort of level. And the other reason to go with this is that it's something Qualcomm is very, very good at. It's low power integrated digital systems. So because we're an industry corporation, we like to have products to sell to people. And so our first sort of product in this space is actually this design suite of tools to enable simulating and working with these types of spiking neural networks, figure out what types of algorithms they're capable of. And this is important not only for us internally while we're figuring out exactly how we want to build this hardware, but we think it can also be very useful in the scientific community for people who want to model these types of networks and people who may want to use this software to help them actually do some science. And so I was very happy to be at a corporation where that sort of potential collaboration is very highly thought of and highly sought after. And so one advantage of these tools is that you can actually simulate much larger networks than you could imagine simulating with conventional means, because we've written our own software language and it'll have hardware that these things run natively on. So finally, I wanted to show you one demo of some of the types of behavior we think we have figured something out about, and how we've implemented those. So I'm going to show you a demo here. It's going to have a robot in it. This robot is going to be exploring an environment and figuring out where certain patches on the floor are. And then at some point, we're going to reward the robot in one of these patches, and it's going to start exploiting the fact that it gets rewards at those patches. And the important thing here is not that you couldn't do this with another programming language or in another, with a normal computer, but the point is that we programmed this thing once at the beginning and program the learning algorithms. And so throughout the video, it is learning this in real time as opposed to something that's been coded up to do this. So here's the patch of the floor. There's our mobile robot. This is running with our implementation of these networks on hardware. So it's learning where all these different squares are. And now we're going to tell it good robot when it goes to the white square here. And so now it has built up this map of where all these things are, and it's going to go and explore the white squares. So I just wanted to point that out as something that, this is a fun demo, but we're hoping to take this technology sort of to the next level as something that you could use not only for mobile robots, but in your own phone. You can probably imagine some of the uses you would have for that kind of thing. So thank you.
Well, I was just going to say, my name is Joan Goldberg. I'm with Strategic Assessment and Solutions, formerly with the Cell Biology Society. Since I don't have an engineering-oriented imagination, can you give us a couple of examples of what that technology might do?
Well, the basic technology would be learning algorithms. So the idea is that if you had a personal assistant, it could start to do more learning of the types of behaviors or things that you have with your phone. It could start to predict maybe when you would turn your phone on, and could ready your applications. Things like that would be really one of the big applications we're looking at.
I just wanted to say I'm really excited to hear what Qualcomm is doing, because a lot of our pension funds own your stock. And I never knew what the company did, and now I feel really, really good about it.
Have you ever thought about spinning out in your own company at some point?
Yes, that's something that I didn't, that's another thing where when I was in the academic environment, that was, even though I was an engineer and had known people who had done this, it still seemed like that really hard thing you did once you were established and had free time. But now that I'm more in this market, that's something that I definitely see as a possibility.
One of the things I learned, I was asked to give a talk to the women in bio, and I thought, oh, we probably sit around the table, 6 or 8 of us, and it turned out to be 350 people. And these women, most were CEOs or CFOs or COOs of their own companies, and it was quite amazing about that.
Sure.
What's the environment for you and other women like at Qualcomm?
Well,
are there other women at Qualcomm?
Yeah, I'm so glad you asked. We are actually on the Working Mothers list of companies to work for. I would say that there's probably about 20% are women overall at Qualcomm, and I looked up this statistic after Madeline's talk, about 17% in the top executive levels. So I haven't done the research extensively, but I have a feeling that's probably better than other places. But I would say in general, it's very inclusive. I mean, one thing about Qualcomm is it was founded by 6 university professors from UCSD, and it really keeps that sort of collegiate environment within the company, and there's also very strong ties to UCSD. And so, for example, one of the things I got to do is they have funding mechanisms for students at UCSD, so I sort of got to, work on picking, who should get the funding and things like that. In addition, they have in-house ways for you to, if you have a new idea, you can propose the idea, and there's sort of an internal peer review, and the top ones will actually get funded, and you'll get time to work on them. So it's a very, I'm not really sure how unique that is. I know Google does some of these things. I think in the technology fields, it's maybe not that unique, but certainly for broad industry, it probably is a pretty unique atmosphere. But yeah, I would definitely say that that it's a great place to work for women.
I just want to make one more comment to your academic friends who said you're off the cliff.
Uh-huh.
I know so many women in chemistry who started their careers and had distinguished careers in industry and then became full professors without having to go through all of that crap. So
Yes.
just let me
Yes.
say that, you make your success there, and then every university will want you as a full endowed professor.
Yeah, and I have to say, when I was making this decision, I was, one of the things that made me feel much more comfortable about it was knowing that Caltech had in fact hired people back from industry as professors, and so, yeah, it's definitely not a one-way game.
Great. Thank you, Blythe. Very good.